dynamic analysis is going to be referring to the analysis of a model for dynamic loading, and it's going to be calculating the stresses and the displacements with that dynamic loading. In RISA 3D, the analysis of the model for dynamic effects can be considered composed of two parts, the dynamic analysis and the response spectra analysis. So we'll go into today's webinar kind of talking about that in two sections. The dynamic analysis will be referring to the calculation of the modes and frequencies of the vibration of the model, and the response spectra analysis will be using these modes to calculate the forces, stresses, and the deflection of the model. So as an overview of what we're going to work on today, we'll be talking about that natural frequency and finding that fundamental period of the structure, and that's going to be our really first stab in what we're doing here with the dynamic analysis. Beyond that, we're going to try to help define those dynamic mass. In order to get an accurate model, defining your dynamic mass is very important. Going from there, we'll take that all into the response spectra analysis. So building codes and are requiring you to follow the response spectra using the mode shapes here to find a envelope of a solution, a total of the dynamic response to an earthquake event of some sort. Or some kind of vibration that's going to be causing the structure to vibrate. And the other point I would like to make sure we hit is troubleshooting your model. Lots of times people have questions about their model. Sometimes they're pretty easy to figure out. A couple different tricks I can show you along the way on how to make that model work better for you. And then lastly, we are implementing time history into RISA 3D version 14. We're right at the end of that development there, so I can give you a quick preview of that as we get there. Okay, so talking about RISA 3D, we have several solvers of the dynamic analysis inside of RISA 3D. And kind of the first one to start out with is the standard solver. And you'll find these solvers, they're actually, if you look here, this is the global model settings here listed. And if you click on that, you'll see that this is the solution tab, which you're probably all familiar with. But you've got an advanced tab, it's kind of buried. And you click on that advanced tab, and inside there's the dynamic solvers. And there's 3 of them listed there. The very first one is the standard solver, and I've listed that here, and that's the subspace iteration to solve for the eigenvalues. These are going to be kind of our standard solver that we started with, RISA 3D, when we added dynamic analysis, and pretty easy. It just goes through. It does, obviously we've got large verification problems. We've worked with this one, so standard solver is a great first step, but we made an improvement on it. We took that standard solver and we improved it by adding 3 different types of solvers, and we called it the the accelerated solver. And it goes through these 3 different types of solvers. The program actually finds which one's going to be the fastest, and then goes and uses that based on what is the speed better for the efficiency. So we typically default to accelerated solver. You can always go back to standard solver if you want to in order to compare values maybe with other programs, things like that, but the accelerated solver will give you an accurate result, and it is most used there. So that one will be kind of our standard. In the latest version here, 13, we added RITS vector solver, which is the last one. And that one's going to be the load dependent RITS vector, is actually going ahead and solving that using what we shortened it to just say RITS vectors. And that one helps you to get a model that run a lot faster, and there's times when your model is going to be very stiff, so this might be a good choice for you. A very rigid model might help you to get better analysis, and we'll see. We actually switch to RITS vectors kind of later in the presentation, and I'll show you how that will help you. So that one's kind of in your back pocket. RITS vectors is there. But the other thing, as we move towards time history, RITS vectors was one that we'd want to have as well. Okay, so we've got our solvers in place. I'm talking a little bit more here. What are the steps to design your model? So using your dynamic model, kind of just breaking it down pretty simply. You're going to build your structural model just like you would, drawing in all your elements that you're going to be part of your lateral resisting system. So we've got that in place. Then what you're going to do is you're going to start to worry about your seismic mass. So either you're going to use your seismic weight, or you're going to apply mass to your structure. and I'll show you that in a couple of seconds here. Right after this slide, we'll talk about more about mass. But the ASC 7 section 12.7.2 is what we're going to refer to as that's the section that would govern for this mass that we're defining. We'll also talk here, the next step would be to, once you have your mass defined, you're going to then go ahead and perform an eigensolution, and you're going to verify how much mass participation is in your model. So we always will continue to talk about 90% mass participation, and that's going to be governed here by the ASC 7 section 12.9.1. So the code governs that you are going to hit that at least 90% mass participation, and that's your code reference there. Once beyond that, we're going to go ahead and perform a response spectra analysis. And so these steps are all kind of, you actually can do them all quickly at the same time. This number 3 and number 4 are actually going to happen at the same exact time. But this is a separate, you're going to pick the response spectra analysis that you want to run, typically based on your code or wherever the jurisdiction of your building or structure is. That's going to govern what RSA you want to select. And then you run that, and that will all happen while you running the dynamic analysis. And lastly, once you've performed 3 and 4 together, you're going to get the results of that dynamic analysis, and you're going to apply it to the structure. So you're going to scale that those forces that you found from your dynamic analysis in 3 and 4 and apply it to the structure, scaling it based on the RSA results. You can scale it back. We'll see here coming up how you can scale the factors to either be closer to the ELF, so equivalent lateral force method, and you can also adjust it to be in the inelastic, or we can see here I over R is going to be our inelastic results. So you can scale those forces, and then lastly, you're going to take that and run it in a load combination directly. Instead of using your EL or earthquake load, you're going to use our seismic loads, or it's going to be our S for seismic, and then X or Z or Y depending on the axis you're applying it to. So you have these steps that you're going to run through. This is a lot of steps, 6 steps, but it's pretty quickly that you'll end up getting down to the bottom. But along the way, you'll want to consider the different code references, and you want to make sure that you are hitting what you need to be doing there. So let's see, and lastly, again, designing that forces and making sure that the members are actually adequately designed. So the next step here really is to talk about loading the structure. So you've built your model. Let's say you've gone ahead and built that model, and now you need to actually apply some loads to the structure. So you want to apply loads, and if you're familiar with RISA 3D, you've obviously done point loads and line loads and distributed loads, area loads, all sorts of things like that. But what we're talking about there is a load. So you can apply a load directly to the structure, and that load will be converted into a mass. So when we're talking about seismic, or earthquake loads, we're talking about the mass of the structure. So, and how that vibrates, so that anything that is considered a vertical load will be just converted directly into, in 3 directions, X, Y, and Z, a mass. So that's kind of an easy way, since the program will automatically do that for you. You can just take anything that's considered a seismic weight and define it as a load, and then the program automatically changes that for a seismic mass. One thing to consider, though, is that the self weight of the structure is not automatically done for you. So you'll want to make sure you apply the self weight either by using our quick Y directional. If it's vertical in the Y direction, you can just put a -1 in there, and I'll show you that here in a second, or you can apply it individually, but you do need to apply the self weight directly. You've got the other option you can do is a mass. So if you're going to try to maybe separate the load so that it's more of a discrete mass loading at the nodes, since RISA is going to be doing the loading here directly on the nodes, you would be able to lump the mass either directly into the center of the structure, center of mass, or you can apply loads directly to the elements as a mass for their own self weight distribution. There's kind of a bunch of different ways you can do that, and you can see when you apply a load, this is just a point load here, I've got, a joint load, you'll see that there's typically you're going to be using this is a load, but you have the option to do this as a mass. And in there you can say, hey, this is a mass, and then you can apply the mass directly to the structure. You can also apply a mass moment of inertia. That's another approach to do it. So if you have any case where you need to apply a rotational mass directly to a location, distribution to account for maybe spatial distribution, for rotational, torsional modes that you want to account for. You can apply it as a mass moment of inertia. And you do that, you could calculate this. I have some formulas here on the right, and this is in the help file as well, that shows you what maybe the diaphragm looks like, the center of mass, and what you would do to calculate that mass moment of inertia. So all sorts of different shapes that you'd be doing. And you could calculate that and then just drop it in as a load, or excuse me, a mass directly as a mass moment of inertia. So mx would be the mass moment of inertia. And so that's kind of an approach as well. Let's take a look at this in RISA 3D. So we're going to work with it as an actual real model to understand kind of how this works when we go over to RISA 3D. So here I've got RISA 3D model. Let's take a look. I'm going to just rotate this a bit, and you can just see just kind of an L-shaped building in RISA 3D, and it's just going to give us the ability to apply, let's just render this a second, and apply this loads directly to the structure. I've defined a couple different ways. So the three different methods I have listed here. So you can see I just have a area load directly on the structure. So that is going to be just our typical load. So DL, and that's an area load. You can see here, so let's just apply that. And this would be the first way to apply your loads, just saying that we applied loads to the structure as an area load. You'll notice I do not have any self-weight in there. So I'm not applying self-weight in this model. If I wanted the self-weight of the actual materials too, I'd need to put a -1 in there for the Y gravity. So this is assuming that this area load's already accounting for all the self-weight of the elements I've modeled. So this 0.8 kips per square foot is my gravity dead load, or my seismic mass. One thing's going to be important, if you look back at that section I mentioned about the dynamic weight of the structure, there's several things you might want to consider. So the dead load is important to be considered. Additionally, you can do your storage live load. That's required here. It says in the ASE 7 you have to do 25% of the floor live load needs to be included in the seismic mass for the storage live loads. Also permanent partitions, you need to account for actual loads if you have permanent partitions in there. Also snow load. So in regions where you have higher snow load, you want to open up the ASE 7 and take a look. It's going to be typically here 20% of the uniform snow loads in certain regions. So you want to make sure you have that dialed in. It's also all for your seismic weight. So going beyond that, you can see I've also applied directly to the structure here. If we go back to our basic load cases, you can see I've applied, there's a center of gravity. I have applied directly a load. So that's going to be, but this is instead of a load here, we would want to do it as a mass. So if we're doing it, let's see here, so we open this up, and this is going to be, this is actually as if it's still as a load, we can keep it as a load. That means the program is going to take that and convert it into the 3 directions for us. And so the next one, if we go to the center of gravity using the load here, if we also do the mass instead of a load, we apply it as a mass. That would be, this here my is telling the program that we want to do that moment of inertia mass as well there. So we have a load and a moment of inertia directly to the structure. And so that kind of helps you see that if you see that the load is directly there applied to the structure. So now we can run a dynamic analysis. So if you click on the solve button, you can see here, we will click on the dynamics right on the last option, second to last option here, and it will solve here based on the eigensolution, so number of modes you select, and then we're going to start with the gravity dead load here. So with gravity dead load, that's the first one where we applied just that area load directly to the structure. So the area load's creating a line load to each member, and then we're doing a nodal mass load there. So every time we hit a node, that distributed load is converted into each node, and then it'll be each direction. So if we solve that, I'll come back to the response spectra, but we'll make sure that all of them are checked on, and all we do is just click on Start Solution. It's going to run through that dynamic analysis and finds those 3 modes for us. So we've got frequency period here, and then we see here we've got the participation in each direction. So what we're looking for by code is going to be higher than 90% participation, and we see here that we do find 99%, so almost 100%. It's really kind of evenly distributed there, so very easy for us to find this 99% for this structure. But we see some dominant modes happening. Looks kind of like we're seeing a couple local modes in this direction here in the X direction, which makes sense for our model. And then we have kind of one dominant mode here, 88% in that direction. So this is going to be based on our loads, applying it as a load. Let's take a quick look and we'll run it as instead of the load here, we're going to apply it just directly as a lump mass in the dead load combination and solve it that way. I'm going to say rerun it with a new solution and it will clear that out. And now we get about 100% in those two directions. And this one here is just kind of there's not much frequency, it's just going in as 0 and it's just dumping into the base there. Because we're creating that in all three directions, we're seeing that extra one happen at just a 0 and that goes right to the base. But we see 99% here. We see 99% on that side there. So these are going to be two dominant modes that we're seeing. There's going to be this kind of a very easy way to see it just dump directly into the structure, and then we're getting those nice dominant modes. The third way we can do it, I mentioned here, was that the other way we say solve, and we can click and do the moment of inertia. So this is going to be lumped with the inertial terms. And we click on that one and say start this solution, rerun it with a new eigensolution, rerun, and we can see we also get something very close where here we have a couple more dominant modes, and we can look at the actual mode shapes here too. So the periods are very close. In this structure, it really doesn't make much of a difference of how we chose to do this, but what I wanted to do is demonstrate the different ways you can do that, and then you can do it on your own in your model. So depending on the type of model you're looking at, you may need to do it different ways. I would say the first approach is always to use the easiest, so just use your loads based on your seismic load there. And then if you have to go to a mass, you can walk down that path as you needed. Let's kind of jump back here. Let's take a quick look at this simple model to understand the period of the structure. We're going to be looking at just a single degree of freedom, SDOF, so we kind of abbreviate that in this structure just to sort of understand the entire process. We're going to go into a more complex structure, but it's easy to look at this starting out. So we see here on our screen the equation for a period. So it's going to be T is going to be representing period, M is going to be their mass, and then K is our stiffness. So starting out here, that's just your simple equation. We go forward from there, and we can see that we can go into what mass is. So mass is going to be represented by the seismic weight of the structure divided by the acceleration of gravity. So we have, in this structure, I'm going to just be modeling this in RISA 3D, and the way I'm going to show that is just going to apply 10 kips to it. I'm going to actually neglect the self-weight just to make this easier for us to understand the hand calc. And then the gravity is actually defined in our global parameters. So we can see that inside there, and you can change that if needed. We've also so here in this example, I've got 10 kips applied to the structure. So that seismic weight is just divided by gravity, and I've got that calculated out here for me in mass. The next thing to find is the stiffness. The stiffness is actually found in the structure by applying a 1 kip or a unit load applied laterally to the structure. The trick with that, if you're using an AISC method or the newer methods, is to turn off the direct analysis method so that you don't adjust the stiffness in any way, just to go with a straight analysis and find that deflection. And we can apply a 1 kip lateral force to the frame here, and then we find that lateral deflection, and that gives us a deflection per unit force here listed as just 0.131 inches. And I'll show that in the model. We'll run a quick test on that. So using all that, you go back into the period equation here, you calculate your stiffness, your K value is going to be listed there, so your K is 7.63, and then we put that back into the equation at the top. And we solve that to get our total, which will be a period of 0.366 seconds. So kind of a quick calc for something hand calc, but we can jump into RISA 3D to see how this actually works. So jumping over back to RISA 3D here, we can see in RISA 3D I have this frame which I described. So I have 5 kips on each node applied vertically down, and we can just see that here if we run that. Let's take a load combination. We've got that that's defined as our seismic mass. So it's really important in order to create your dynamic model, you need a load combination using your seismic mass. So it's always a good idea just to do a separate load combination to understand just that seismic mass. Oftentimes people either overemphasize, go with a conservative route and over apply dead loads, things like that. But when you're using seismic mass, you want to go exactly with what you've got listed there for the mass. You're not going to apply anything but your mass in that actual load combination there, and that is going to be what we use to define that dynamic analysis and finding that mode shape. So that lateral stiffness I had mentioned earlier, that was to find our stiffness, so we could just run a single combination to find that. Using our joint deflections, we can find what that stiffness there was. This is our joint deflection for our top node, N2 and N3 are moving in the x direction 0.131, and that's how we went ahead and found that K value. So using that K value, and we back calculated it to get our period. Now here in RISA 3D, we can validate that period by going ahead and doing a dynamic analysis. So we're going to go ahead and use the equal sign solve here, and instead of doing the load combinations for static, we're going to go to the dynamics and pick that and say solve. And we can choose here on the top the eigensolution. We can choose now, the biggest piece I mentioned here is to do that seismic mass. So you select that one load combination you defined here for the seismic mass. And I'm going to I don't need to turn any of these on. I'm going to keep those off and just say start solution. When I say start the solution, it goes ahead and it creates 3 mode shapes. And in those 3 mode shapes here, we're determining the different frequencies and periods for the structure. So we had calculated in our hand calcs, we had gotten that period to be 0.366. And we can see here on that first mode shape, we have 100% participation in the x direction, and that's the period that we defined. So we can validate that hand calc there that we did. So it's a nice, easy way. And you can also, nice way to see that is to also, besides just the spreadsheet, it is really nice to see it in actual visually. So you can go to plot options and go to the deflection and go back to the mode shape here. So when you're looking at the mode shape, you can pull up any of the mode shapes you created. So I had 3 mode shapes. We're going to look at that mode shape, that first one, and I can animate that shape, and we can see it animated. It's pretty exaggerated animated, but we can slow it down if we wanted to. We can speed it up. So you can see all sorts of that mode shape. And this is really the mode shape being deflected and showing on your screen is important so that you can see how it is that mode shape, especially if you have any local modes that are happening versus the entire model going there. So we have 100%, so we see that all happening. You can also show it, you don't have to show it as we see here, just deflected, not actually animated, and that's helpful as well. So let's move to a different model to investigate the mode shapes and the natural frequencies further. Opening up this model here, it's a little larger, and we can see some different aspects on this model. And we're going to be looking for the natural frequency of this shape, of this model, and the different mode shapes. So the ASE 7 is going to require us to get a 90% mass participation, at least. So it's important to understand how to get that mass participation and a little bit farther about what the mass participation is, but also to understand the natural period. So different parts of the structure are going to be activated at different natural periods. So there may not be a single natural frequency in the structure. This is what makes the dynamic analysis so valuable, is that you can take the natural frequencies of each portion of the structure and combine them to get an overall dynamic response. And that's what the ASE 7 is requiring. So in this here, if we look at this model, I'm going to just kind of flip it around a bit. You can see in this direction here, in the x direction, we're regular, very regular structure, but in the z direction here, when we're looking at this, we're seeing that there is going to be some mass and stiffness irregularities because we've got a brace frame on the lower level and a moment frame above that. So we're going to be seeing that it's going to change the behavior of the stiffness, and this would be considered something you might need to do a full dynamic analysis on due to that, as the ASE 7 requires. So what I'll do is, I mentioned here, if we looked at the global parameters in the solution tab, there's an advanced button, and I mentioned there's a dynamic solver, so you can choose the accelerated, standard, or the RITS. I'm going to stick with the accelerated solver on this one, and you can see that gravity acceleration I mentioned is listed there as well. So I'm going to say OK. And what I'm going to do is we have already our seismic mass defined. So if we look at the structure in the seismic mass, you actually see a little bit more load on the lower level as well. So we've got some extra point loads happening. Again, that's going to help contribute to the different irregularity in the structure. So what we'll do is we'll go ahead and push the solve button, and the dynamics is what we're looking for. So the static stuff is on top, and we have the dynamics section here. I'm going to push solve. And the eigen solution is listed here, and you choose the number of modes you want. So in this model here, 10 is kind of going to be my first guess for that. Seismic mass, I need to select that, and I have that already defined. So that's my seismic mass that is displayed right now. And then I can go ahead and click on the start solution. I'm going to just keep all of the spectra already turned on for response spectra analysis. And really there, all we're looking for is just mass participation, and we won't get into spectra just yet. So I'm going to click on start solution. And it's going to run through, and it gives me a overall view here of the frequency and the period. And we see for each mode shape, we're going to have different participation. So in that X direction, I said it was pretty regular. We're seeing a mass participation of 90%. So that's going to be a dominant mode for that structure. And so that helps us kind of understand that X direction, and that seems pretty logical. In the Z direction, we're not seeing that type of behavior. So we're getting only 48% of mass participation in that one, which is a lot, but it's not close to the 90 required here. So we also see 40 and on that mode shape 8, and then they sum together to hit our 90%. So we're getting the numbers ASE 7 requires, but we can see a little bit why that is happening if we go into the plot options and display this. So clicking on plot options and looking at our deflected shape, we can see the mode shape. And the mode shape here, we'll look at that second one, which was that 48% participation. And I'm just going to show this here. I'm actually going to turn the loads off, and we'll look at this here in this direction. And so what we can see in this one is that we've got mode shape 2 is going to be showing us where the upper two floors are going to be in phase with each other, and then the bottom floor is going to be just kind of remaining still. So that's kind of showing us that first one where this is about 48% mass participation. If we let's go ahead and switch over to mode shape 5. We can see mode shape 5 behaves in such a way that the top two floors are going to be moving out of phase with each other, and that the lower floor here is going to be still. And then if we jump to, I think we had our last one was going to be mode shape 8. And we can say OK. And in that one, we see that the upper two floors are remaining still while the bottom is moving significantly. So the power of this is that we can go ahead and combine all of those together to get a dynamic analysis for the entire structure. And ASE 7 is going to require that whenever you have anything in the case where the equivalent lateral force method is not going to give you this type of single dominant mode shape that you can just assume and go with. So we're going to actually take more of a fine-tune approach and look at this in each mode shape and then sum it together. Let's take a look at this model in order to understand the scaling factors and for the response spectra analysis. Let's just quickly open up the response spectra. I'm going to see there's a library here. And if you click on that, you'll see that there's response spectra analysis. We see a variety of different codes listed here. And this library is already defaulted with the program. You can add your own spectra. But if we just take a quick look, let's look at the ASE 7 2010. You can view that database. It does require that we have some different properties in here. So you need to put your SD1 and your TL values inside of the program here to look at this spectra. You click on OK. And then you get to see it in a tabular format. So we see that it's got the parametric design shapes here, and we see the period and the acceleration. And you can switch between frequency or period as the left side of this, or you can switch between the acceleration, velocity, or displacement on the right side of this. And we can see a variety of different information for that. That's helpful. You can print that out, but what also is really good is to see this in a plot format. So again, in the same type of thing, you can enter in the parameters for that building location and say OK. And then we can see here that we've got a plot. 4 is giving us a triplot. So this is going to be giving us a plot of the 3 different parts here. So you're seeing the acceleration, the velocity, and then the displacement, and that's all plotted on the frequency here. You can also do this as a single plot, again entering those values in, and you can switch between the spectra, different spectra values, and then if you want it linear or log there, you can change that, and you can also change the time or frequency there, period. Again, you can change the different pieces. So it's helpful in order to see the different ways on a graph. But you can also, if you're beyond what we're looking at here for the building codes, you can look at that and by adding your own spectra directly in. So for us, we're going to work on just this one here using a known spectra. So I'm going to push close. And the first thing you'd want to do is jump into the seismic tab here and fill out the information for the building, or structure. So you're going to put in the CT and the factors here. So for us, we have an R factor of 4 in this model. That's an important piece. And then we're going to want to put in your SD1, your SDS, and I have mine already set in here, S1. And then your period here, the long period listed there. So when you put all this information in, it's saved in for our scaling factor, and that will help us with our response spectra. So I'm going to say OK, and we'll go ahead and run the dynamic analysis. So this model actually has a seismic mass defined. We saw that a little earlier, this similar model. So I'm going to go ahead and say dynamic analysis using the seismic mass. And we're going to calculate 10 modes. We'll go ahead and you'll say the extraction analysis. You can select from this list what you need there. So we'll actually pick the 2010. We get that 2010 listed here, and I'm going to pick all the 2010. And you can go from there. We're going to use the combination method. We're going to use a CQC. You have the ability to use SRSS, or the Gupta methods. All of those can be chosen. CQC is going to be the most common method, and that one, it helps us to get a more accurately account for the response spectral analysis for closely spaced modes in the periodic frequency range by directly summing them with each other. So we also see that we could have done the square SRSS, which is square root sum of squares, and that's kind of closer to your hand calc method, not as much used anymore in design practice. And then we also have an ability to do the Gupta. And this one is really for when you've got more of a structures with significant rigid content. So in our model, we're going to go ahead with the CQC. I'd like to point out a couple of these options here. So under the spectra, when you choose the different directions, you have something called use dominant mode for signage. And what this is about is that a lot of these procedures here are requiring us to do a summation. So we're doing a summation, and what happens is you end up with a value that has no sign. So we see that our forces are just either all going to be positive, and we don't have a direction for the signage of that. So what we've done in order to make sure that the actual results match closer to what we would expect by statics is we have a checkbox here that says use dominant mode for signage. And what that does, it merely looks at the reactions for the mode that has the highest percentage of the mass participation, and then assigns a positive or negative sign to each joint reaction based on those results for that individual mode. So then a mode, we can see here, it can have, when we have a dominant mode that's maybe like 70% or greater, we can see that that is actually going to be the sign. So we see dominant mode, and that is higher than 70% of mass participation, and then that would be the sign that we'd be attributing to it. So that would help us give our information on our results and understanding our results better. Another option I'd like to point out here is the calculate residual mass checkbox right there. So when we're running a response spectral analysis for the seismic design, the response for high frequency modes can be calculated and found without having to solve for their individual mode shapes. So we can do this to save some time and the memory of the model, especially if we have a larger model. This can be helpful when you have structures that have a large amount of mass in the lower levels of the structure, or also very rigid modes, that we can go ahead and solve and to find the 90% participation without having to get to those specific eigenmodes. So this checkbox helps us to find that, and it will give us some information above and beyond the number of mode shapes that we've actually calculated. So I'm going to actually, in this model, since we don't need it here, I'm not going to turn that on, but that can be helpful, especially as we get closer to time history. So now what I'll do here is I'm going to say start solution, and I'm going to run this model with 10 shapes, and I'm going to go ahead, and here we got 10 mode shapes, and we see that I have, we saw this from earlier, I have 90%, over 90% for both directions. So we're at the point where we want to keep moving past this to get more results. So with our mode shapes in hand here, what we can do is go to our load combinations. We're going to go to the data entry tool and load combinations. And in here, we have the ability to add some loads. So I'm going to just delete some of my loads already in here, delete marked lines. And you'll see that on the top there, there is a scaling factor. So Spectra scaling factor. If I click on that, I have the ability here to see some information. So first of all, it's going to give me the static base shear based on, if I push calculate, based on the values I entered in just before here in the global parameters. So those are grayed out. I can't edit them at this point. But what I can do here is say calculate the loads, and it's calculating just the equivalent lateral force method. So it's going to go through and calculate all of the different values for the period, hand calc period, and really what we're looking for is that base shear in the different directions. So I've got that all listed here, and it's going to calculate that, and it comes right back in. Then this is going to be our unscaled base shear. So this is going to be based on our mode shapes here. So we've got calculate that, and now what we can do is we can scale these. So instead of applying this directly, the code allows us to scale this back, and there's a couple different things here. So if I'm just going to open up the help for a sec so we can see some of the code references while we're right in the program. And that's a really good thing too while you're working in RISA, is to push the help so you'll see exactly where we're pulling these values from. So there's a base shear multiplier here listed in for several different codes. Specifically in the ASE 710, we can see it is in 12.9.4. We've got a 85% scaling factor. So we can scale those forces back by 85%, and then we're going to calculate the scaling factors directly based on some limits. So we have what we have here is called ELF, or equivalent lateral force. We have a limit to calculate that up to, and that would be just that base shear multiplier multiplied by the static base shear, and then all divided by our unscaled base shear. So we're taking a variety of these different numbers to calculate that ELF limit. We also compare that value to the I over R, which is going to be just your safety factor, that your divided, or importance factor, excuse me, divided by your response modification coefficient. So the R. So those are going to be bringing us back to an inelastic base shear calculation here. So we're getting those two numbers, and then whatever is going to be the largest there is going to be our scaling factor there. So we can use our controlling value. So we see here we're picking between these two values, and that's what's being applied, this lower number. You can always override all of this by just entering in your own value. But what I'll do here is you want to check this box to say apply these safety factors, and when you do that, you can say OK, and it'll go back in. Now, I do want to create some different load combinations first. So in order to create load combinations, you can use the load combination generator. So looking at the load combination generator, you can apply all sorts of different items in here. We can say it's going to be a non-orthogonal and it's reversible, and we're going to also say that it's going to be X and Z. So we can create all these different load combinations, say generate, and you'll see here that the program is going to use ELX instead. It's actually going to be using we want to, instead of use ELX, we actually want to use our response spectra results instead. So we would be using SX instead. And instead where we see ELZ, we would be using SZ. So we've got that available right here when we click on those. So you'll see you want to just replace those versus what you have listed. And a quick and easy way, you can just copy and paste. And I'm going to go ahead and do that right now real quick. I'm just going to control, copy, and paste these where I see them there. So you can just, and the easiest way to do these, you can either copy it out and put it into Excel, but you can see it takes me just a matter of seconds in order to copy and paste, and I'm just using Control C and Control V. Okay, so once we've got all of our in place, our earthquake, we're now using we want to go back to that scaling factor and calculate it and just apply it to all of our, so you'll see our scaling factor SF is going to be applied wherever I see my Spectra analysis applied there. So you got that all running ready to go. So at that point, you're now applying these loads directly to your structure and you're ready to solve an envelope solution. So it looks like I cleared my solution, so let me just go ahead and solve that one more time. And I'll solve all those mode shapes there, and then I will go ahead and apply, and I can solve the envelope, and it's going to be applying all of these directly to the structure. And then what we can do is we can look at our design results. So now we see specifically for the load combinations where we created different items here, we can see that we've got maybe some failures. Looks like our single angles need some help. They're overpassing here, so we can go through and then go through design of those angles as we need. I want to talk about troubleshooting different models and understanding what to do when things aren't as you anticipate them. So first, just kind of talking about mass participation. We talked a lot about 90% participation rule and getting that per the ASE 7. And what we're trying to do there is to see that we can get a summation here based on the code requirement. So I'm looking at this quick screenshot. We can see I've got 10 modes and I don't hit that 90%. So what can I do to help that? A couple different things you can do. The first thing you can do is to add more modes. That's kind of a simple and easy way. Just maybe we default to 3. You can move up to 10. You can move up to 100, 200 at the max there. Depending on the model, sometimes this is a little less painful if it's a smaller model. If it's a bigger model, maybe that's a little harder because it takes a little bit more time to run. But it is the quickest way because you can just change the number there, run the model again, and see how many modes contribute to get that percentage. Another thing you can do is discretize the mass. So if the way you're applying that load is not adequately getting the loads directly to the structure, and it might be lumping too because there's things like walls are going to be stiffer and they might be drawing some of the loads. They're more rigid, so they're drawing some of the loads to them, and different elements can cause issues where you're just not seeing mass participation. So I can show you a quick method to discretize the mass, and that's in the next model here I'll show you. The other thing you can do is add axial tensile torsion, so you can try to draw in that torsional effects using mass moment of inertia or different, like locating different loads in different places, but that's another approach. The other things to do is to switch the solver. The RISA solver really does help a lot in finding these things, and that, as this is a new feature in version 13, you may not be used to trying that, but you can also just try to switch the RISA solver. So what I'm going to do, let's hang on here. I'm going to switch over back to RISA 3D. In this model, we can see that it's going to be just a RISA 3D one floor with walls in one direction and brace frames in the other. You can just kind of see here we've got a concrete wall, steel brace frames. We've added plates for like a semi-rigid diaphragm. And then let's just run an analysis to sort of see where we're at. So I've applied here self-weight to the structure. So just applying that self-weight, actual self-weight directly to the structure, and that's just -1 in the y gravity. That's all I'm really doing here. So if I solve this model using the self-weight, going to dynamics, and we can say pick up here actual self-weight, and I'll just do 10 mode shapes since that's kind of a typical way to do it, and we're going to solve all 3 directions and say start solution. When I run this, we can see here that come up here. So we do get a mass participation of over 90% in the z direction, but we don't get it in the x direction and we don't get it in the y direction. So the reason they say the x direction is insignificant compared to the y's and the mass in the y direction, and that's because the shear walls are going to be very stiff in the x direction versus the vertical direction. Whereas we see the vertical direction here, we're going to see a lot of local modes because we've got tons of these little local modes happening in that. So we don't see an overall, dominant mode happening in the structure. So we see like this is, if we look at this kind of in the different directions, what's happening here. So if we look in this X direction is kind of in and out of the page, and we see that these are going to be our shear walls direction. So that's along the loads here. So we see in the X direction we've got the shear wall contribution. It's very stiff on both sides. Let me scroll this around a bit. So what do we do to fix that? And the one type of way you can do this is using what I said, discretizing the mass. So instead of using just that self-weight, we can actually apply the self-weight manually to the structure. So if you look at this, what I've done here, I'm going to go back out of that, is that at every point you would calculate the mass of that structure and then reapply it manually. So the weight of the wall, you can see it's going to be applied as a line load. Any beams that are framing in or columns, you can take that as point loads that you would apply as point load directly on top of the columns. So you can solve the model just by running it as a single combination with that self-weight, find the mass, maybe find here the joint reactions, and then just move them up on top of the columns. So that's a way to do it, and if we do that, this is already done for us with several different line loads and point loads. We can solve the same model using dynamic analysis. Again, instead of trying to do it as a self-weight with a -1 in the y direction, we'll use the discretized self-weight. Do the same exact solution, and we can start to see it wants to ask us if we want to rerun the solution. I'm going to say use a new solution and solve it. And now we get a lot better in the X direction. So we're getting 94% in the SX, we're getting 99% in the Z, the Y, we're at 55. We can try increasing this maybe to a larger modes. Let's go ahead and try that and see if we can get up higher. So instead of 10 modes, maybe we'll go to 100 and start this one more time and see if we can get it to go a little bit farther than what we just had. So it's going through all the different spectra, and you see it just takes a little longer. This is again a simple model, but we do see that it takes just a significant, noticeable time longer. So hopefully you can get away with smaller modes so you don't have to go through this, but we are taking a lot of information down here. So on the Z direction spectra, we'll see, there we go, and we can scroll all the way to the bottom, and we now get a total of 99% for SX, SY, and then 100 for the Z. So we're getting a lot better numbers here as we increased it and as we discretize the mass. The other thing we can try doing is, this is a third option, and as I mentioned, you can go to the RISA vector. So going to the global parameters, you can go to advanced there, and switching from the accelerated solver to the RISA vector solver, saying OK. And we can then go ahead and solve this. And I'm going to switch it back to just the self-weight, the actual self-weight, so the easy way to do it. And then we'll go ahead and say apply it in these directions. And let's just go to 10. Let's say 10 for starters. I think we should be okay. Let's see. Running it with just 10, we get pretty good. We're getting a lot better. One of the things we can do is let's go ahead and increase that back to 100 and see if we can get closer to, without having to do the discretization, and say start solution. It'll run through those same, and here we go again. It goes and breaks it down for us, and running through and finding all of the different response spectra analysis. So this is using the self-weight I mentioned, so it's a little bit easier for us to do. It's a -1 in the y direction, just one step, and then you can go ahead and see what the results are. So we see as that solves, we can scroll down below that, and we get 96, 94, 96%. So we're getting really the best answer there. So discretizing the self-weight was really a popular option before we had RISA vectors solution. But at this point, you are basically getting all of that done for you. So it may not be something you'd want to do, since it might take you a little more time. But it always is there if you need. You can know how to do that. You can run the solution and apply the mass at the top of the columns and the walls. So another model here I'm going to jump to, hang on. Let's go ahead and open this model here. Is going to help us to see a little bit some of the issues when we have some troubleshooting of why we're not getting some participation. So this model is a little different type of frame, not so little symmetric, but it's got lots of little things going on in it. And what we can do in this model, let's look at the steel. It's just a steel collection of a frame. And in this model, I have applied, let's look at our seismic weight. So you can just see just the seismic weights applied in the load combination as a dead load. It's a load with an area load, and it's got the self-weight of the actual members as well. So we're just applying those loads directly to the structure. And using that, we can go ahead and say, do the dynamic analysis. And let's go and say it's going to be just, let's say you start with 10 mode shapes and start the solution. And you'll see here when it runs through, let's give this a little question. Let me open up and pause. It's going to give us the natural frequency here and it gives us the period, but it does not give us much participation. So we've got 4% in each direction. So again, what I said is go ahead and increase the modes. So we'll actually go up to the 50 modes and see if we can get a little bit better on that. Say solve that and run through 50 different modes, and we'll see what we get there. So we still are not getting quite as good as we want. We're pretty close, but we're not good enough. So what you might want to do at this point is really investigate why you're not getting such great mode shapes there. I'm going to go ahead and turn this back to wireframe. I'm going to turn those loads off. And we might just make note here of the ones that we have. So, 7, 1, 7. We do have a contribution higher with let's see, 13 and 20 and 19. So let's look at what those mode shapes look like. Looking at your deflected mode shapes can help us understand so what's going on in there. So let's look at 13, for example, and let's animate the shape. If we say OK, we can see it really looks like it's locally that mode shape is very local. That's happening on our 13 mode shape there. Let's go ahead and close that down, and we'll go and do plot options again and just kind of scroll through some of these. Let's open up our frequencies here in the background. So maybe 19 is one we want to look at, and we can say what that looks like. Again, we see kind of just a small local section is going to be deflecting, and not quite the entire global. So one of the things that's happening in this model, if we go back to just the view and turn off that, is that I have braces, and I've also have nodes at those braces. And I mentioned that that this is a nodal mass contribution. So whenever you are applying loads, they're being applied at the node, which means that whenever I've got nodes there, those connecting braces, that's causing me to apply some mass there as the loads get distributed through. So one of the things you can do is maybe turn off that node location right there by deleting those nodes. Typically, they're not really needed. If you needed to brace these at those locations, you could just do that manually for the design results, but you don't need to actually put a node so that those actually contribute to each other. Typically, X braces don't contribute at their X's there. You don't usually connect them. So you can delete a lot of these here. I'm just going to delete all my nodes that are going to be causing this crossing. What that does is sort of just eliminates all those nodes, as I mentioned. Hopefully, we see that kind of cleans this model up, and we get to see a little bit better global contribution of that mode shape versus the local. So just a couple more, and pretty easy. One of the things too is why did we have nodes there? It's kind of a typical modeling thing where people just do a model merge and it can create nodes for you. You can actually, there's options so that you don't create those nodes, and it's a good thing to sort of, even if you're doing a static analysis, maybe to not create those nodes. So now if I solve the model using that dynamic analysis one more time, using the seismic weight, and then we can go to the 50, we can say start solution and run through it, and we see some better numbers, and what we do see is 92% is happening on those there, and we start to see some larger global mode shapes here, so like 80% in that one. Let's take a quick look at that one. So that was mode shape 2, and if I go to mode shape 2 on this, let's see, we might see what that shape looks like better, and we start to see the whole frame is actually deflecting versus just kind of a one little section flying off. If you're familiar with static design, where you see maybe just a portion of your model fly off, that usually tends to see that there's kind of an error in your modeling. And that kind of brings up some good point too, is that you do need to make sure that your model runs as a static analysis. So it is always a good idea just to start out with your load combination self-weight and just take a quick look at your self-weight and see what's happening in the structure. If it's unstable, it won't run in dynamics as well. So you want to make sure that statically it's stable and then go to the self-weight, run that dynamic analysis. That's a common problem where you're just completely, the model's unstable before you even go to dynamic analysis. So let's go back here to the presentation. Time history is something that we're going to be adding to the program in version 14. So I'd just like to take a couple minutes here and show you a preview of what's to come out in the next version. So jumping over to RISA 3D. In RISA 3D, we can see here that we've got just a simple frame model, a sample building, and the data entry toolbar here added a new item called time history loads. So if I open that time history loads, I can see I have the ability to apply time history loads directly to all of the joints. We can specify specific joints. Let's take a look here. This is going to be the El Centro earthquake representation, and if I open that up, I can see the pattern loading here and review that by opening the view. And in here I can see the loads that are going to be applied here, or actually this is going to be based on the acceleration, based on the time. So we can scroll across that. You can add your own or generate your own. I'm going to use that one, but we can see here this is going to be the value of acceleration versus the time, and that's going to be applied into our structure. So I'm going to close that down, and in order to do that, I've already run a dynamic analysis based on the seismic mass, and then I also applied this time history load in this load combination 3. Running through that load combination, we can see here I'm just going to go ahead and just run this single combination, and it goes through and solves through all of the time history solution and through steps. On the lower portion of my screen is doing the load steps. You can see it pops through, it goes through a whole series of different steps, and it's going to take through about 5,000 different steps in order to accomplish this here. So we're going to fast forward past that. And it's almost finished here with our last load steps. As we approach the end, we can just see here the results are going to come up on our screen. And my joint reactions here, I see everything is based on this load combination and load step. And beyond that, we see all the different forces that are happening in the structure. We can then now also go and trace. So if I click on the trace button, I can click on any joint in the structure, and I'll see the behavior of that joint over time, the displacement of that, and we see where it bases the time. So as I scroll across, I can see that I'm going to be getting these different values. I can see that on the chart as well as on a spreadsheet format. You can export this, you can change the different times. So if we want to kind of focus in on maybe 5 seconds versus all that we were saying about 53 seconds, we can see the time a little bit closer and we can get more granularity inside of that. We can export this as well. I'm going to close that down. We can also see it graphically on our screen, which is nice. We can go to the deflection tab and we can display these graphically. We're going to see the animated shape, and let's go ahead and open that up so we can see the whole thing. So we see the whole shape is going through an animation. We can control the speed of that animation, and we can really see how that behaves during this earthquake. And we can also apply a trace to that. So we can choose a member we want to look at, a node. So this node here, we can maybe type in F6 underbar 3, and we'll choose that here in the X direction. It's displacement. And at the bottom, you can see as the model is displacing here, we can see that over time what's happening and what the displacement is for that one joint. So it's really helpful to understand all of that. And that's just a quick look. We'll kind of get into that more as the feature gets released.